I don't know what my mega favorite number is. I don't even know whether it can exist. I do know that my mega favorite number, if it does exist, is greater than 1 million, perhaps substantially so, and I know it ends with 3, 7, or 9. My mega favorite number is a prime number. The number before it has 2 factors, and the number before that, 3 factors. The next numbers before that have 4, 5, 6, and 7 factors, respectively. So how big is this number? The smallest number with 7 factors is 128, so it has to be larger than that. But there are many numbers between 128 and infinity. Is there a way to find out the answer without brute forcing all the strings of numbers between 128 and 1 million? Luckily, factors come in certain patterns. We can't have 2 prime numbers next to each other, and we can't have more than 3 two-factor numbers in a row. So naturally, that narrows down the possibilities for our string of numbers. As we look closer at the string, patterns emerge, and these emergent patterns tell us just how high we would have to start looking to find this number. We can use some basic deduction to know something about this string of numbers. Our prime number is odd. The number before it must be even. It has to be the product of 2 and a large prime. That 2-factor number has to end in 2, 6, or 8. It can't end in 0 because then the odd factor would have to end in 5, and if it ends in 5, it would have to be divisible by 5, and it only has 2 factors. And because it can't end in 0, our prime number can't end in 1. It has to end in 3, 7, or 9. If we go back to our 3-factor number, it has to have 3 as a factor. In any string of 3 numbers, one of them has to be divisible by 3. Our prime number is not divisible by 3. The number before it has 2 factors, one of which is 2 and one of which is a large prime, so it doesn't have 3 as a factor. Therefore, our 3-factor number has to have 3 as a factor, as well as 2 other primes, one of which at least must be large. Our 4-factor number is also divisible by 4 because every other even number is divisible by 4, and we know our 2-factor number is not. It might be easier to make some conclusions if the pattern continued, if we knew our 5-factor number is divisible by 5, but that is not the case. The 3-factor or 4-factor numbers could be divisible by 5, but if we keep on looking backward, we know the 5-factor number is not divisible by 2 or 3. We also know the 7-factor number is not divisible by 2 or 3. And if we count backwards from our prime number, which we know can't end in 1, we can see that our 7-factor number can't end in 5. That means that its smallest prime factor would be 7, and there is only one number under a million that fits that description, 7 to the power of 7. We can quickly ascertain that 7 to the 7th is not followed by a 6-factor number, so we will have to look over that to be able to find a candidate. How far up the number line do we have to go? Finding numbers with this exact factor and pattern is rare, and as we go up higher, it becomes more rare as numbers with even more factors come into play. Around 1 million, we have numbers with up to 20 factors. And the more we miss and the higher we go, the more will appear and the harder it will be to complete our sequence. There may be emergent rules that prohibit this pattern from ever happening. And this is just an example. There are many numbers between 7 and infinity. If it is that difficult to find a sequence like this starting with 7 factors, imagine the complications of 15, 63, or 739 factors, for example. Also, if this pattern does it occur once, many times, or an infinite amount of times? Despite the seemingly simple arithmetic used to examine this problem, it quickly shows emergent behavior that makes trying to solve it quite difficult. But, if nothing else, parsing numbers like this is just as fun of a way to fall asleep as counting sheep. I hope there is no obvious mathematical errors I made in this video. If there were, let me know.